All right, let's get into it. Today we're tackling a really cool, kind of special case for graphing rational functions, the slant asymptote. This is the last piece you need to really master the whole picture. So, you know how graphs can flatten out and approach a horizontal line as they shoot off to infinity, right? But what if a graph goes to infinity, but instead of flattening out, it follows a perfectly straight, tilted line? Yeah, that can happen. And that, my friends, is exactly what a slant asymptote is all about. Okay, so to really get our heads around this, we first need to do a super quick refresh on the rules for horizontal asymptotes. It all comes down to one thing: comparing the degrees of the top and bottom polynomials. So here are the three big rules, right? You've got bottom heavy, where the denominator's degree is bigger and the asymptote is just y equals 0. Easy enough. Then you've got when the degrees are equal, and you just take the ratio of the leading coefficients. But look at this last one, the top heavy case. When the numerator's degree is bigger, there's no horizontal asymptote. And that's where things get interesting, because that's exactly where we need to look today.
So, inside that no horizontal asymptote world, there's this very specific, special situation that gives us a slant asymptote. And it all boils down to one simple, super strict condition.
So what is a slant asymptote? You might also hear it called an oblique asymptote, which is just a fancy word for tilted or slanted. It's just a straight line, but it's not horizontal or vertical. It's the line that your graph gets closer and closer to as x flies off to positive or negative infinity. Think of it as the tilted runway the graph is trying to land on, but it never quite touches.
And here it is, the golden rule. The one thing you have to burn into your brain. You only, and I mean only, get a slant asymptote when the degree on top is exactly 1 bigger than the degree on the bottom. Not 2 bigger, not 3, just 1.
That's the magic number, 1. If the difference in the degrees is anything else, you can forget about a slant asymptote. The graph will do something else entirely at its ends, but it won't be following a straight tilted line. Okay, so we know when to look for one, but how do we actually find the equation of that line? Well, it's time to reach back into our algebra toolkit and pull out an old friend, or maybe an old enemy for some of you, polynomial long division. Honestly, the process is super simple. 3 steps. Step 1, just double check that the degree on top is exactly 1 more than the bottom. Step 2, do the polynomial long division. And step 3, and this is the best part, the answer is just the quotient. Whatever you get on top of the division bar, that's your line. You can literally just throw the remainder away. Ignore it completely.
Let's look at a quick example. Say you have this function here. You do the long division and you get a quotient of x plus 3 plus some leftover remainder. Well, guess what? The asymptote is just y equals x plus 3. That's it. That's the tilted line that our graph is going to follow forever.
All right, enough talk. Let's get our hands dirty and actually do a few examples. Seeing it in action is where this stuff really starts to make sense. Okay, first up, a kind of sneaky case. If you look at this one, you might notice that the numerator actually factors. And check it out, the x plus 1 on top and bottom just cancel out. So what we're left with is just the line y equals x plus 2. The graph is literally a straight line, just with a little hole in it. So in a way, the line is its own asymptote. All right, now for a more typical example where we have to do the work. The degree on top is 2, on the bottom it's 1. The difference is 1. So we know for sure there's a slant asymptote. Let's go find it with some long division. Okay, let's set up the division. First question we ask is, what do I multiply x by to get 2x squared? Well, that's got to be 2x, so we put 2x up top. Now we multiply that 2x by the whole divisor, x plus 2. That gives us 2x squared plus 4x. And just like regular long division, we're going to subtract that whole thing. So after we subtract, we're left with just x. We bring down the next term, the minus 3, so now we have x minus 3, and we just do it all over again. What do I multiply x by to get x? That's easy. It's just positive 1. So we put a plus 1 up top, and our final quotient is 2x plus 1. So we finished our division. We got a quotient of 2x plus 1 and a remainder of negative 5. But what did we say about the remainder? We don't care about it. Just toss it. The slant asymptote is simply the quotient, so our answer is the line y equals 2x plus 1. Done. Now this is super important too, knowing when not to look for a slant asymptote. Check this one out. X cubed over x plus 1. The degree on top is 3, on the bottom it's 1. What's the difference? 2. Is that exactly 1? Nope. So there is no slant asymptote here. This graph's end behavior is actually curved. It follows a parabola, not a straight line.
Okay, let's wrap this up by talking about the two biggest mistakes people make with these. If you can avoid these traps, you'll be in great shape.
Okay, mistake number 1, keeping the remainder. People do the division and then try to include the remainder in the answer. Don't do it. Remember, that remainder gets put over the divisor, and as x gets huge, that fraction becomes basically 0. It's irrelevant. The second big mistake is thinking that any time the top degree is bigger, you get a slat asymptote. Not true. You have to check that magic number. The difference must be exactly 1.
So you might be thinking, okay, that's a neat math trick, but am I ever going to use this? And the answer is yeah, you might. This idea actually shows up in the real world, especially in places like business and economics. Think about a company making, I don't know, smartphones. They have huge fixed costs at the beginning, right? The factory, the machines, all that. So the average cost per phone is really high at first. But as they produce millions of them, that initial cost gets spread out. The average cost function for this situation often has a slant asymptote. That slanted line represents the long-run cost per phone. It tells you that after all the initial costs are absorbed, each new phone adds a steady, predictable amount to the total cost. So there you have it. Slant asymptotes are fantastic for telling us the end game of a graph, where it's headed as it goes off the chart. But that leaves us with a pretty big question, doesn't it? The asymptote maps out the long road ahead, but what about all the interesting stuff that happens in the middle? How do we figure out all the twists, turns, and bumps along the way? Well, that's the next part of the story.